evidence for the Big Bang. So the SQA quotes a final bit of evidence for the Big Bang, but they get it wrong. This so-called evidence which they quote is called Olber's paradox. He was a German guy. But yeah, he got carried away and it's actually a false proof. And I don't know why the SQA have put it in as proof of the Big Bang, but it's wrong. So Olber's paradox, Olber's question was, well, imagine you're on Earth and you're looking at any direction in the sky. Every single sight line, every single direction, every single millimeter or less than a millimeter of sky from Earth will surely end with a star. And so the night sky should be filled with light, because it doesn't matter what sight line you look at, there are such an infinite number of stars in the universe that every single sight line will end with a star. So why the hell isn't the night sky dark? And his so-called suggested answer was, well, those stars, in the majority of these sight lines actually, are moving away so fast, their light has been redshifted so much that the light is invisible. So rather like the background glow of the cosmic microwave background radiation. He thought that any patch of the sky, any little millimeter in the sky which is dark in the night sky, is because the star which lies there is moving away so fast that the light it must inevitably be giving out has stretched and it's invisible to us. Now, it's wrong. It's not even a paradox. It's a wrong assumption. Every single sight line from Earth does not end with a star. Okay? Why? Well, stars have a limited lifespan. And in any case, space is far too enormous for stars to be able to fill it up like this. There aren't an infinite number of stars. Yes, there are a lot of stars in the universe, but space itself is enormously bigger. It's vastly more vast. So this notion that every single sight line must end with a star is rubbish. There's not enough stars in the universe for every single sight line from Earth to end with a star, and stars have a limited lifespan. So even if there was a star on a particular sight line, it could very easily have died by now and so not be giving out light. So this isn't really proof of the Big Bang, because this idea that it's showing that loads of stars are actually giving out light which is too redshifted for us, that's a false assumption. It's a wrong assumption. Not every single sight line on Earth does end with a star. So the real proofs of the Big Bang are Hubble's observations and the cosmic microwave background. So Hubble's observations, think raisin bread. Cosmic microwave background, think about microwave light from every direction. Now we're getting small. So in the 1800s, let's think about the state of science. So in the 1800s there was this idea of different types of tiny ball-like building blocks called atoms making everything up. You learn so much stuff in school which is sort of crammed down your throat that I think you can not appreciate the significance of science. So, you know, the idea of why anyone would be interested in this is sometimes lost, but sort of quite philosophically, if you know, it's quite a philosophical question, you know, what is stuff made of? You know, if you think about even what you experience in your everyday life, you know, you think, well, why is a lump of wood so different in feel to a blade of grass? Why, if you touch a stinging nettle, you know, why does that hurt? Why do you get stung? What is in a sting? Whereas you touch any other flower and you don't get hurt. You know, what is light made of? What's glass made of? Why is glass different to, I don't know, carpet? And you can go through your whole life interacting with these materials But at some point, the more interested, intelligent people started asking, well, why are these different things different to touch, different to look at? Are they made of different things? If they're made of different things, what are they made of? So by the 1800s, there was this idea that everything is made up of different types of tiny ball-like building blocks called atoms, and the different atoms were named elements. And the idea, which of course was right, is that various combinations of these different types of atoms give all the various materials in the world their properties. It's a bit like a cookbook with a certain number of ingredients, and if you combine these ingredients in different ways, then you get different foods. And if you combine these atoms in different ways, the theory went, and of course it was correct, then you get things as varied as metal and carpet and wood and glass, plastic. And at this point, there was a bit of a sort of break, and the chemists decided to do a little bit of stamp collecting. They said, well, let's work out, let's find all these different atoms. Let's see how many different types of atoms, how many different elements we can find out. Let's put them in a cookbook. Let's do some stamp collecting, and let's see how these guys combine to make up the stuff in the world. So the chemists started doing things like putting electricity through water, and they found that you get twice as much of one type of gas than you do of another type of gas. And the gas you get twice as much of, which of course is hydrogen, H2O, had very different properties to the type of gas you only get one part of, which was the oxygen. And then they realized that these two different types of gas were two different elements, called them hydrogen and oxygen, and put them into the periodic table. And this is what chemists did. Chemists love a nice bit of stamp collecting. Physicists were getting a little bit more philosophical. They said, okay, it looks like the world is made of atoms. What the hell are these balls? What the hell are these atoms made of? So the first sensible suggestion was a guy called J.J. Thomson. And it was about this time that big batteries were being created and electricity was vaguely starting to be almost understood partially with what's going on and what you need to make massive batteries and this sort of stuff. So with massive batteries, he found that he could pull tiny negatively charged flecks out of some materials. Now I said negatively charged. Charge was known about vaguely by this point. The guy Benjamin Franklin, who did dangerous experiments flying kites into thunderstorms, worked out there was two types of electric charge. He called them positive and negative. He could just as easily have called them type A and type B, or type 1 and type 2, but he called them positive and negative. And J.J. Thomson realized that some materials, if you put a massive, what we would call electric field on them, you can pull out negative flecks. And these tiny negative flecks he called electrons. So if you have pulled these tiny little particles, electrons, these negative flecks, out from atoms, as he's shown that it was possible, then it showed you that atoms were not this uniformly hard solid balls made of this singular stuff. It showed you that atoms must have internal structure, part of which were electrons, but there must be other stuff left behind. Now he knew that overall stuff, atoms overall, a lump of something, doesn't have electric charge, and yet he managed to pull out these electrons, these flecks, he called them electrons, these small particles, and he could tell that these were negatively charged. So therefore, if the overall atom normally has zero charge, then if you pull out the negative, then that shows that part of the atom is negative, so the rest of the atom must be positive. So he decided that atoms are a big positive solid lump with tiny negative electrons embedded. And because the positive and the negative were the same size, they cancelled each other out, and so atoms were normally completely neutral. They didn't have a charge. Alright. Now this was known as the Thomson plum pudding model. A plum pudding is a very old pudding made of sponge and then plums embedded in it. And the plums were the negative electrons, and the sponge pudding was the positive background. You might think of it as a spotted dick model. The plum pudding was like a Victorian pudding. Spotted dick was a famous pudding from like the 1950s and 60s. Same sort of thing, but a sponge pudding, but with raisins in rather than plums. Anyway, you can think of it as Thomson's plum pudding or Thomson's spotted dick. The idea that atoms are made of negative flecks or electrons within a solid positive. And it sort of made a lot of sense, and you can see why he came up with that idea. Meanwhile, what were the others doing? The chemists were continuing to make their menu of different types of ball, their different elements, and they put this into the periodic table. Guys like Mendeleev and all those who the chemists worship. Biologists, well, God knows, they were probably colouring in and labelling pictures of plant cells by then. Hooke had invented the microscope, and so they were collecting leaves and looking at leaves under the microscope and drawing out pictures of cells and colouring in cells, much as biologists do today in biology lessons. And by this point, physicists had started playing with radioactive stuff. Radiation had been discovered, and they were blasting stuff with radiation, because why not? This was long before the days of health and safety, and they were kind of firing in lots of radiation to big lumps of things to see if they could make them hot, or to see if they could turn the material they were blasting with radiation, make it radioactive itself, to see if they could turn it into anything else. So that's what physicists were doing, and one of the main guys who was doing this was a guy called Rutherford, who was a New Zealander. Now, most of these physicists were just firing in radiation into great big blocks of stuff, just for the mad bounce. But Rutherford decided to go the other way. He decided, well, what happens if we fire radiation at a wafer-thin bit of material? And so he got something called gold foil. Or rather, he got his students to do this, and then he took the credit. But he got a really, really, really thin bit of gold. He used gold foil rather than aluminium kitchen foil, because you can make gold foil much, much thinner. And he fired a bunch of alpha particles at it, which is a type of radiation. And they maybe thought, well, if something's really, really thin and you fire radiation at it, you're firing loads of energy at it, it's probably going to heat up. There's probably going to be radiation effects. What they actually found was that the vast majority of these radiation particles went right through this thin wafer of gold. But once in a while, they didn't go through in a straight line. Once in a while, one of these radiation particles would be deflected. And then, once in even more of a while, one of these radiation particles would bounce right back the way it came. Now, if you have the idea that matter was made of spotted dick model or plum pudding model, that there were some of these negative flecks called electrons inside absolutely solid sponge positiveness, then this didn't really make much sense. Surely the radiation would become embedded in the overall neutral, but it would be embedded in the sponge cake bit, and it would probably just make the whole thing a bit hot. But it didn't really explain why loads of stuff was coming through, and it's like, well, and what about this bouncing back, and what about this being deflected? Spotted dicks didn't explain that. So what Rutherford decided was, because most of this radiation goes straight through, essentially atoms are made of nothing much, except in the middle of an atom there has to be something really small and really hard and really positive. Because it has to be really small, because only once in a blue moon does the radiation bounce right back. It has to be really hard, so that the radiation bounces